Okay, so this will be the last class of this semester that I will give a lecture. And this Thursday we will do the final review. Uh, we will review the what will be covered and uh, what will be the questions like in a final exams. Alrighty, and the topic for this last lecture is about NP-Completeness. So some of you may have already heard the term NP-complete or NP-hard stuff. So it's a term that is used to basically to describe the difficulty of algorithms. Okay, so the whole chapter that we're going to cover is very theoretical, and it deals with a systematic way. It provides a systematic way to describe how much time it requires to solve certain problems or to implement certain algorithms. Okay, so I would encourage you to read the chapters after the lecture because uh, what we're going to go through in the slides are pretty limited, and there won't be a lot of math involved or proof involved, but the textbook provides more contents. Okay, so to start with, we would like to, I would like to introduce several examples that demonstrates how easy and how hard some problems may seem to us. So we have already, in a previous couple of weeks, we have covered, actually we have spent about 3 weeks on the graph algorithms. And the last algorithm that we used, we have been covered using the Bellman-Ford algorithm, and the Dijkstra's algorithm is for solving the shortest simple path, right? The shortest path problem. And if we change the word shortest with longest, then we would have a very totally different problem. Say, given two vertices, or imagine that you're using a map and you want to find the distance or traveling time between your current location and your destination. It's quite easy. Well, easy in terms of it's quite common that you want to find the shortest path, right? But it's not that common if you want to find the longest path between your location and the destination. And it turns out that if we want to compute the longest path between two vertices on the graph, it's not an easy problem. We already know the shortest path problem, right? For Bellman-Ford algorithm, and it will cost us big O of v times e time. And we know that, we admit that this is not a very top efficient algorithm, and the Dijkstra may do better than it, but Dijkstra comes with additional constraints. There shouldn't be negative weights on the graph, okay? But comparing it with the longest simple path problem, the shortest simple path problem is not a difficult one, because if you want to find the longest path, there are way more different options, way more alternative paths you want to try, you need to try, right? And merely to determine whether a graph contains a simple path with at least a given number of edges is hard, not to mention the longest path problem. Okay, say you can try that. If we want to find, let's work a little bit on this simple example here. If you want to find the longest path between the source and the destination, say Z, then we need to like consider a lot of possible ways, right? We can, because either like if we first check how many vertices are connecting to S, we can go from S to T, right? And we can also go from S to Y, and there's no limits, actually no constraints on which way to go, because we don't know which way will lead us to the longest possible path, right? And from S to T and T to X, T to X, right? Or T to, well, there's no other ways, or Y to X or Y to Z, or T to Z, right? So the more vertices we have in the graph, the much more bushy our search path will be, if we're going to like use a search algorithm to find possible ways that connects the source and the destination. Okay, so because you want to find the longest path, then you will need to iterate over all possible paths, and there's no um, easy way to use greedy approaches like the simple shortest path problem. Okay, this is one introductory example. And the second example are two problems that we haven't introduced in our lecture yet, but let's go through them briefly. The first one is called a Euler Tour, okay? And it's named after the famous mathematician, Euler. So a Euler Tour of a graph, it's basically a cycle, okay? But that cycle requires that we need to go through each edge exactly once, okay? For example, in this graph, we need to start with some vertices and end at some other vertices or the same vertices. But all we need to do is to go through all the edges exactly once. We don't want to go repeat ourselves. So I think the solution for a Euler Tour is quite easy to get. We can determine whether a graph has Euler once we have gone through all the edges, examined all the edges. Okay. For example, let me try if we can find the Euler path on this example. Oops. Right. For instance, if we try from this edge, 2, 3, 4, 5, 6. Okay, so I believe that is a Euler path. So, and it's basically that you start from some vertex and you start your path, and you need to go back to itself. But I remember, if I remember correctly, we need to count the inbound or outbound numbers for each vertex, and there's limits on the number. So we need to keep the inbound number to be an even number. Even number is preferred, but an odd number is also acceptable only if there are two, if and only if there are two vertices that has odd number of inbounds. So anyway, a Euler tour is not a very difficult problem to examine. And actually, we just need to go through, check each edge and the connecting vertices for once. But the Hamilton cycle of a graph is a slightly different in terms of definition. It's a cycle that visits each vertex exactly once. Okay, then that is it turns out to be a totally different problem. So maybe we can try to find it. on the same example here, like we start from here, oops, start from the middle and connecting to this one. Yeah. So through this pass, we exactly visit each vertex exactly once. And it seems not a hard job here, but actually, if we look at the examples on the right, on the um, qubit-like example on the right, then actually determining whether a graph has a Hamilton cycle is not as easy as Euler Tour. Okay, so this is a second example. And let's look at the third example. So it's a type of problem called conjunctive normal form, or CNF for short. So we'll look at a 2 CNF versus 3 CNF satisfiability problem. Okay, so this CNF problem uh, deals with a Boolean formula. Okay, it takes a Boolean formula that contains Boolean variables. So those variables can only be 0 or 1. And you can also use the Boolean connectives, like the and, or, and not operators. Okay. And so we say that a Boolean formula is satisfiable if there exists some assignments of the values 0 or 1s to those variables. And our goal is to cause the whole formula to evaluate to 1. So if there exists such assignments that makes the whole formula evaluate to 1, then we claim that this formula is satisfiable. Okay. So this also, we have the numbers 2 and 3 before the CNF. So the meaning of these two numbers is that, so if the formula is a K-conjunctive normal form, then it means it is the end of clauses of ORs of exactly K variables. So I guess using a simple example would be easier to see. So a typical 2 CNF is that we have uh, a bunch of OR clauses, right? We have 3 OR clauses, and they are all connected by the AND operator. Okay, so within the parentheses, they are connected by the OR operators. Okay, and each OR clauses only have 2 variables, and that's why we call it a 2 CNF. And there's no limit on the number of AND operators. Okay, so for this particular example of the 2 CNF, we can, for example, assign x1 to be 1 and x0 to be 2, to be 0, x2 to be 0, and x3 to be 1. And we can easily check that the first OR will evaluate to 1. Okay. And the second is also evaluate to 1. Okay. And the last one also evaluate to 1. So if we use AND operators to connect 3 1s, the result will be 1. So the whole conjunctive normal form will be satisfiable. Okay. So, and we can imagine that 3 CNF is a connection, is a bunch of OR clauses connected by and within each OR clause, there are 3 variables involved. Okay. But we can actually found a huge difference in terms of how easy it is to solve the problem. A 2 CNF satisfiability is can be actually solved within polynomial time, okay? But a CCNF satisfiability cannot, okay? So we first look at this polynomial time definition. So we say something polynomial function like a function f of n is polynomial if it can be described by like n to the power of something, right? Then this is a polynomial time. And if we recall a little bit about the sorting times for the running time for sorting algorithms, it's n times logarithm of n for the most efficient algorithms we have implemented so far, right? And so the polynomial time, say if k equals 2, then it's a quadratic running time, and we are not happy with quadratic running time. And if k is even larger, then we are also don't think it's a very sufficient algorithm. But in the case here, we would be um, um, less stringent, will be less strict about the running time. So if it's a polynomial running time, then we can basically consider that, okay, we will accept this efficiency, okay, because it's better than polynomial running time algorithm, or even higher, even functions or even higher orders, okay? All right, so we have seen these examples, and we can see that even if it may be a problem that seems quite easy to deal with, but it sometimes will turn out to be a difficult problems that requires a lot of computation. Okay, so based on the examples here, we will look at three classes of problems. Okay, so the first is called P. And in these problems of this class P are solvable in polynomial time. So the capital P is for polynomial, okay? And that means they can be solved by big O of n to the power of k time. And the k is a constant, and the n is the input size, okay? So any type of sorting problems belong to this class P, because we know that a logarithm function is for sure to be at a lower, a logarithm function always grows slower than a polynomial function, okay? So sorting algorithms belongs to class P. And actually, basically, all kinds of algorithms that we have come up with a reasonable solution belongs to this class. Okay. All right. So I highlighted the solvable part because now let's introduce the second type, NP. And those problems are verifiable in polynomial time. Okay, so the verb verifiable, the adverbs, adjectives actually, solvable versus verifiable is different. So by being verifiable, we mean that if we are given a solution to the problem, then we could verify if it is correct in polynomial time. It's not to solve the problem, but it is that we are given something to verify, then we can verify it is polynomial time. And of course, to verify something is easier to actually solve a problem, okay? So in theory, we can assume that the class NP should be a bigger subset, okay? And NP should have a broader range, okay? Because if a problem is P, then we can solve it within polynomial time. Then of course it can be verified. Any solution can be verified within polynomial time. But for a problem that can be verified within polynomial time, it is not necessarily the case that we can solve it for sure. Okay. So that's why we have the third type, which is called NP-complete. And any problem within this type means that it is a problem in NP. Okay, it can be verified. It can be verified within polynomial time, but it is as hard as any problem, or it, it is the hardest one among all NP problems. Okay, so this is how we define the NP complete. Although currently it's still a vague definition, but we basically need to use the first two classes, P and NP, to define the third type, NP complete. Okay, so basically NP complete means that NP complete plus P will complete the total NP set. Okay, so that's where the name comes from, NP complete. Okay, and some intuitive understanding of NP complete can be that those are the most difficult problems that we can think of for this. Well, under the condition that the solution can be verifiable, okay, within polynomial time, but to solve it is really hard. Okay, so there can be some formal definitions for these terms used in these vague definitions, such as the as hard as. We can use formal language to describe the problem, but we are not going to do it here. If you're interested, you can refer to the textbook, but I don't think the textbook also offer a complete definition. Okay. All right. So having those three types laid out, and unfortunately, the status of these three classes of this NP-complete class is unknown. And that means, well, no polynomial time algorithm has been discovered yet for any NP-complete problem, nor has anyone been able to prove that no polynomial time algorithm can exist. Okay, so it's a very unknown status. Like, we haven't found anything, any polynomial time solution to a NP-complete problem, but we also people didn't prove that no polynomial time solution can exist. So it's really an unknown issue in theoretical computer science. Okay, so I think you can use this to help you memorize the currents, actually the relationship between P, NP, and NP-completeness. And there's some vagueness in the definition of completeness, NP-completeness at this point. But intuitively, this is already a useful tool for us to help identify easy problems versus hard problems. Okay, so to put it in a more plain language, we can think of that the class P are those problems that can be solved quickly, and the class NPs are those that can be verified quickly. Okay, and we know that it is more difficult to solve a problem from scratch than to verify some clear solutions that are given to you, right? So NP should have a larger range scope than class P. Okay, so it makes sense to imagine that these two are two different types, or it makes sense to believe that NP should encompass P. So NP should include P, and P is a subset of NP, but people haven't proved it yet. Okay, so all the problems that we have introduced in this course, they are in the class P, like sorting problems, like the dynamic programming problems, like the graph problems, they are all class P's. Okay. Um, Even though for those not really sufficient uh, efficient algorithms, like those running in quadratic running time or in cubic running times, they are belong to the class P because we have found the solutions in polynomial time for those problems. Okay, and here are some guesses or how people assume the relationships between these three classes. So first of all, any problem in P is also in P. So that is for sure, okay? Because if we can solve it in polynomial time, then given a solution, we can verify it in polynomial time for sure, okay? But for now, we can believe that P is a subset of NP. But whether this is true is still an open question, okay? And also, if any NP-complete problem can be solved in polynomial time, then that means every problem in NP also has a polynomial algorithm or polynomial solution. Or if you want to prove that P equals NP or P doesn't equal NP, you can say that if you want to if you solve the one NP problem, then basically all NP problems can be solved within polynomial time. Yeah, but people haven't found such a solution yet. Okay. So now most people, most theoretical computer scientists believe that NP-complete problems are intractable. Like basically we cannot find polynomial time solutions to them, right? But no one has ever discovered a solution yet. But also, on the other hand, no one has found evidence to completely rule out the possibility that NP-completeness are solvable in polynomial time. Okay, so again, this is a very vague area. Okay, it is still unknown, uncertain yet. Okay, so if we want to visualize some guess, then most people would believe that NP and P are different types of problems. Okay, so if P doesn't equal NP, which means there's some space that are in NP but are not in P, and those are called the NP-complete region. Okay, and also in these plots, there's another term NP-hard, which we didn't theoretically we didn't officially introduce here, but you can think of it. It's outside the range of NP-complete, which means they can be even harder problems. Okay, and for the second guess, if P equals NP, then that means all NP-complete problems can have a polynomial time solution, and then P and NP they totally overlap. Okay, but in most people would believe that they would believe that the the relationship on the left is more possible, more likely to exist. Okay, so this is the figure from the textbook. So people would believe that the figure in A, this is the most unlikely. Okay, so and the figure in D are most likely. So people believe that the NP should be a larger region than P, and there's a overlap between, so the overlap area between the co-NP and NP are the NP-completeness parts. So here the co-NP actually means those problems for which there is a polynomial time algorithm that can verify no solution, like to verify a counterexample. Okay, So that's what most people believe. And I think this figure D is kind of similar to the previous slides, the figure on the right, the figure on the left. Okay, figure on the left. Oops. Right. So there should be some NP, P shouldn't be totally equal to NP, and that's the most common belief. Okay. So if we want to summarize the problem, then I would think one figure like this would be enough. So both the P and the NP completes are wholly contained by NP problems. Okay. All right, so we have provided the definitions for the three classes, and the purpose basically for having such a classification is that it helps us to identify easy problems versus hard problems. Okay, then if we can establish a problem as an NP-complete one, then we basically have very good evidence to say that this is intractable. This is an intractable problem. And if we are solving some practical problems, then we want to avoid putting too much energy, putting too much time in solving those intractable problems. Like we would prefer developing some approximation algorithm, or we want to solve some subsets of the problem rather than coming up with a perfect solution to the whole problem, because if it's NP complete, then there's no it is very likely that there's no easy solutions to those problems. Okay, so let's look at a bunch several examples of typical NP complete problems. So the first one is called traveling salesman problem, TSP. And it's basically a graph algorithm. And it's like a salesman must visit n cities. And if we model the whole map with a graph of n vertices, okay, then a complete graph, we can use this complete graph with undirected edges, and every pair of distinct vertices is connected by a unique edge. Okay, so the salesman wished to make a tour or a Hamilton cycle, right? And Hamilton cycle means that we visit each vertex once and finishing at the city he starts from. Okay, and the cost for travel between two cities will be given. Okay, is given by this function, C function. Okay, so the goal is to minimize the total cost of the tour. We not only want to visit each city exactly once, but we also want to minimize the cost. Okay, like it's in this example we can find a solution, right? But given let's look at how easy it is. Okay, so given a solution, it will be a sequence of n vertices. Okay, so the verification algorithm will check this sequence contains each vertex exactly once. Okay, and sums up all the edge costs, and then we'll check whether the sum is at most below some value. Okay, so this verification problem can be this verification is actually quite easy, right? Given the solution, we just need to go through all the vertices once to see if there's duplicates or not, to see if there are repeated elements or not. And also we need to sum up all the edges. So it's quite an easy way to verify, okay? But the problem itself is a NP-Completeness, okay? So now we are not going to show how to prove NP-Completeness, So we will come to that later in the last slide. But here we just need to know that it's verifiable within polynomial time. So that's why it belongs to the class NP. Okay. And the second type of problem is subset sum problem. Okay. So given a finite set of positive integers and a target integer number t, then the question is to ask whether there exists a subset whose elements sum up to t. It's a quite simple problem in terms of definition, right? Given a set, we want to find whether there exists a subset that sum up to some value, right? So, for example, given these integer numbers of that, a lot of integer numbers, then a subset is a solution, okay? But it turns out that uh, well, let's first look at how easy it is to verify. Well, it's quite simple, right? So given the solution, if I give you a S prime and I claim that it is a solution, you can easily verify it. You can just sum up all the numbers in it. If the summation doesn't match, then it's not a solution. If yes, then you're happy, right? So it's a very easy, simple solution, simple verification process. But the algorithm itself, it's hard to come up with a solution within polynomial time. It's actually the NP-Completeness. Well, because you can intuitively think of the problem that we need to examine a lot of possible combinations. Okay. And the last two types are two graph-based algorithms. The first one is called a clique. Okay. So a clique is a undirected graph. The clique of a undirected graph is a subset of vertices, and each pair of the vertices is connected by an edge. Okay, so it's a complete subgraph of G. Okay, and the size of a clique is the number of vertices it contains. So the clique problem is to find a clique of maximum size. Okay, so in the graph here, to show the clip is um, the undirected graph is a subset. So I think in this example, the clique here is the red vertices that the size of a clique is a number of vertices it contains. So yes, so a clique is a complete subgraph. And the complete means that each pair of the clique is connected by an edge. Okay, so given a clique, it's quite easy to verify because we just need to check whether each edge belongs to E. Okay, but the problem to solve it is not an easy one. Okay, so using the definition of the clique, we can also define a second type of problem called vector cover. Okay, so it's a vector cover is a subset of vertices such that if the edge from U to V exists in the original graph, then the edge, then the two ends are also in the subset. Okay, so the size of the vertex cover is the number of vertices in it. So, and contrary to the clique, the vertex cover problem want to find a vertex vertex cover of the minimal size. Okay, for example, the red vertices here covers the whole graph because it applies to the according to the definition. As long as one end of the edges are in the subsets, then we say it belongs to the cover. Okay, so to verify it's quite easy because the two problems, the vector cover problems, is related to the clique problem, but it's not easy to solve. Okay. All right. So we have introduced several NP-complete problems so far, and actually, we can use those different types of NP-complete problems to help prove the NP-completeness. And the technique we're going to use is called a polynomial time reduction. Okay, so it provides a formal ways to show that one problem is as hard as the other, okay, within polynomial time factor. Okay, so what we basically can do is to convert a TSP problem, traveling salesman problem, to a Hamilton cycle, and to a vertex cover, and to a clique, and to a 3 CNF satisfactory, and to satisfactory, and to a circuit satisfactory. So basically, we just need to prove the NP-completeness of the circuit satisfactory problem. Then we will show that all the subproblems that exist in the descendant nodes in this tree are actually NP-completeness problems, NP-complete problems. Okay. So for details, you can read the textbook for the definition of this circuit satisfactory problem. All right. So lastly, let's look at this summary page. So the key points of introducing the NP-completeness in different types of problems is that many problems, it may seem easy or not hard, no harder than the sorting graph algorithm, graph searching algorithms or network algorithms. They are actually NP-complete. So that means if we spend too much time on it, it will be a waste of time. Okay, so if we are able to identify an NP-complete problem, then we can at least make a statement about how hard it is, rather than how easy it is, right? Because it is hard, then we can try to bypass it, like try to prove the existence of an efficient algorithm, and instead because no efficient solutions can be found, and we just need to um, find the approximation to the original problem. All right. So that is so much for the NP-completeness chapter, and I would strongly recommend you to read the textbook. And I think the most one important technical point is that the NP is a larger. Basically, people believe that NP is larger than P, and NP should also contain P. And if a problem is NP, if we say that a problem is NP, it doesn't mean that it's a hard problem, because NP means that a solution can be verified, right? It's only hard if it's NP complete, if we cannot find a polynomial time solution to it, right? So that's our last lecture for this chapter, and also for our whole semester as well. So we will meet again on Thursday, and we will talk about the final exams and answer all related questions. And so sorry, I need to leave earlier, so I will end the